Performance realities, right? So, you guys probably learned in 210, right? You spent a lot of time talking about big O and asymptotic analysis, right? You learned, look, what matters is the end behavior, the shape of the curve, right? But if you're the user, you care if something takes 1 second to run or 1,000 seconds to run, right? That actually makes a difference to you. In the real world, right, constant factors matter. That's not to say algorithmic choices don't matter. If you make a bad choice in an algorithm, the constant factor may not matter at all, right? But having done that, in the real world, constant factors matter a lot of times as to whether or not something is useful or, preferable. In order to deal with this, we need to understand how the system works. We need to understand how programs are compiled and executed, how processors and memory systems operate, right? How to measure performance and identify bottlenecks, how to improve performance without destroying code and modularity and generality, right? The first point, how programs are compiled and executed. Look, unless we understand our tool chain, unless we understand how C code becomes assembly code, we're going to have a really hard time understanding some of the nuance of what's actually running. Right? Sometimes the C code that's generated, the assembly code that's generated from the C code, sort of makes sense. It's what one would expect. Okay? Sometimes it isn't. And being able to go look and understand which compiler flags are generating which tweaks to what's being produced is a really helpful skill. We spend a lot of time talking about caches, right? Talking about the memory hierarchy. Critically important. False sharing, right? How to measure performance. It's really hard to improve performance unless you know where you're spending your time, right? Amdahl's law. The biggest gains are going to be where you're spending your time. The smallest gains are going to be where you're not. And that's really pretty true regardless of how much you can optimize a code section. If the code never runs, it's going to have no impact. If it runs a lot, anything you do that makes it better is going to have an impact. We also want to understand how to optimize code while maintaining it as quality code. It doesn't do us any good, right, to remove every function call in our entire program under the guise that function calls take time. Why jump, push things onto the stack, and return if we don't have to? Well, okay. Maybe that saves a small amount of time. It's unlikely to make any measurable difference, except for the fact that we're not going to be able to maintain a code that's one big blob, right? So we need to be able to figure out what we need to do and optimize it without destroying overall the code modularity and generality. Optimizing compilers provide efficient mapping of program to machine. They allocate registers, they schedule code, they eliminate dead code, they eliminate minor inefficiencies. Right? Optimizing compilers can do a lot for us. What they can't do is pick the algorithm for you. Right? They can solve some of the very small, low-grain problems, fine-grained problems, but not the bigger things. There are also some things that we need to understand they just can't do. There's some optimization blockers that might surprise us. And understanding those will help us to understand where we need to look for optimization. An optimizing compiler fundamentally can't change the behavior of the program. It'd be really unfortunate if your program worked and you optimized it and then it didn't work anymore. Right? You can make it really fast if it doesn't need to produce correct results. And so this is sort of interesting because sometimes there are things the compiler looks at that it cares about that we don't. For example, if we're doing computation with floating point numbers, it understands that floating point numbers have a rounding, so it won't move around the order of the computation because it won't change the way the rounding happens. We now may, however, realize that doing that is within our tolerance. It doesn't affect the correctness of the program for our purpose. And so we can factor out some computations, do them once instead of multiple times, things like that. Most analysis is done within a basic block, within a procedure, something like that. Not across the entire program. A compiler is rarely going to remove a function call, right? It's not the type of thing it does. Most analysis is based on static information. Okay? It has no idea what inputs are going to show up. It has no idea what's going to happen more or less often. All code is equal to the compiler. The upshot of all of this is that when in doubt, the compiler must be conservative. Okay? It can't break correctness. there's some generally useful optimizations. Here we see, inside a loop, we're constantly computing n times I. Notice that I and n don't change. They don't change within the body of the loop. They're constants with respect to that loop. So if we pull them out and create a variable ni that represents n times I, now we do this once instead of n times. We've saved a lot of work. Do you see that? We've reduced what needs to happen inside this innermost work loop, which is going to save time. Okay. And here you can see this happening just inside assembly code. Okay. Where you see that being put into a register and the register used. Reduction in strength. Sometimes the compiler knows that certain operators are faster than others. For example, it knows that left shift and right shift are faster than divide or multiply by 2, or powers of 2. So it'll automatically do that, substituting a faster operation for a slower one. And we've already seen this before. We saw this on one of the earliest slides of the semester, right? So we shouldn't change our code such that multiplying by 4 becomes a left shift by 2. The compiler will do that for us. Okay. Reusing portion of expressions. Compilers are not actually very good at exploiting mathematical properties. They're just not going to sit there and apply identities to figure out what's going on and find some complicated, convoluted way of factoring things out. They can do some simple things, but they are generally very, very poor at that. If you've got some complicated algebraic expression, you might be able to do a better job simplifying it, factoring it out than the compiler can. I plus 1 times n, I minus 1 times n, I times n. We know that this is n, in, and in. The compiler might or might not recognize that. Make sense? Depends on the compiler. We'd be just as, we'd be better off, again, to pull that out, I times n, put that into a register, and then use that register. In times n, minus 1, in times n plus 1, in times n plus j. Compilers generally just accept the function as a basic unit. They won't let functions blend into what's before them, what's after them. Okay? An inline function is different, but a real function is generally an optimization blocker. So if we look at this, this is going to walk through the characters of a string. Okay. And regardless of what goes on, right, it's not going to be able to deal with what goes on before or after this. I can look at this in place, but it can't blend this into what comes before it or what comes after it. And the trick here is that you might look at this and say, well, this is going from I to the length of the string. This is big O of n, this is big O of n, right? Where n is the length of the string. You agree? That'd be a naive look. But if you actually know how string length works, you know that string length walks through the characters of the string until it hits the null at the end. So string length itself is big O of n, and then this loop is big O of n, so it's n squared. Does that make sense? If we pull this string length out and don't call it within this loop, right, this would get much more efficient. Right, if we would simply say length equals string length of s. And then for I equals 0, I is less than length. Now we're back to big O of n. Because we're not computing the length of the string each time. Okay. And this is just showing you the breakdown, of why that's n squared. And this shows what string length does, walks through linearly. This shows the fix. Capture the length in a variable, that way you don't recompute it. And now you can see the bottom line is the improved version. We'd call string length once, and that's the original version where we call it each time. Very clearly, O of n and O of n squared curves. So why didn't the compiler do this? It was obvious to us. The compiler views, procedures as things that don't get mucked with, right? Procedures may have side effects. They alter the global state each time they're called. The function may not return the same value for given arguments. It all depends on what's going on. The bottom line is that compilers do much weaker optimization before and after a function call than they do if there's just regular code there. Make a small function inline, and it serves the human purpose of having a function for readability and reuse, okay? But actually dumps the code off in line to let these optimizations happen. The trade-off is, of course, code size, right? If you've got a huge inline function, that huge chunk of code gets dumped off every time it's called. So if we take a look at this code updates b of I on every iteration. B of I equals 0. B of I plus equals A of I times n plus j. Okay? B of I plus equals I times n plus j, right? Every iteration of that small loop, right, B of I is being updated. Do we see that? On top of that, we see that B of I is set to 0 before the whole thing happens. Okay. Initial value of B, let's say it's 4, 8, and 16. Iteration 0, 3, 8, and 16. Iteration 1, 3, 22, and 16. Iteration 2, 3, 22, and 224. Okay? So the compiler has to consider the possibility these updates will affect the program behavior. Removing aliasing. Anytime we have the same value pointed to or identified in more than one way, the compiler doesn't know what's going on in the second use. Right? It's looking at one use. It doesn't know what's going on in the second use. Okay. Two different memory references specify a single location. It's easy to have it happen in C because of pointers. This allows direct access to storage structures. The compiler now has to deal with this aliasing effect. Hey, put your cell phone away. Busted. Okay. So instead of doing that, if you've got something that is not going to be changed somewhere else, okay, copy it into a local variable. Now the compiler doesn't have to worry about the aliasing because the local variable is not aliased. Then copy it back. It doesn't have to worry about the fact that I have a function, in other words, where A is a pointer and B is a pointer, and both A and B are actually the same thing. Does that make sense? You may look at this and say, I'm not string copying from a string to a string. Right? Anytime I string copy it from the string to the same string, right? I'm copying from string A to string B, which is different, but the compiler may be worried about what happens if they're the same. To exploit instruction-level parallelism, you need to have a general understanding of modern processor design. You need to understand that, of course, it's limited by data dependencies. We can't have parallelism if we actually have real dependencies. And simple transformations can have dramatic performance improvements. Okay. Cycles per element, CPE. Imagine that I have an array. My array has 10 elements, and I'm going to process each of these 10 elements. CPE, or cycles per element, is a measure of how many clock cycles it takes per element of this array on average. In other words, how many cycles did I spend processing the array, how many entries were in it, divide. Okay? It's one important measure of efficiency. So the total amount of time is going to equal the cycles per element times the number of elements plus whatever overhead there is. Okay. So here we have a table that shows the operation add, multiply integer, add, multiply floating point, unoptimized, and optimized with the -01 flag, optimization level 1. And then here we can see the number of cycles per element. And you can see that we have a huge gain, right? About half as many cycles per element. Not bad for a compiler doing things automatically. Okay. What can we do? Well, we can take this call to vector length, sort of like our call to string length, and move it out of the loop. Now we don't need a bounds check each time. We can accumulate into temporary, right? T inside that loop, and then copy T into destination at the end. By doing this, we've now gone down again. This was by half by using optimization. This was to way less, right? What, 1/6? 1/4? By making some very basic changes. We've talked about our cute little modern processor design before. We talked about superscalar. Superscalar processor can issue and execute multiple instructions in one cycle. The instructions are retrieved from a sequential instruction stream and are usually scheduled dynamically. Okay? In other words, modern processors take their instructions, buffer them, and try to dispatch them onto the functional units to keep all the functional units busy. But they can only do that to the extent that they can find, strings of independent instructions. If there's a dependency between one instruction and the next, then they can't have parallelism there. What's the benefit? We get parallelism without having to think about it. Most CPUs since about 1998 are superscalar, and the Intel line since the Pentium Pro. Okay. So now we can see I'm doing A times B. I'm doing A times C. Okay? A times B and A times C are independent. All right? A times B and A times P1 would not be independent. Do you see that? I can compute those first two in parallel, P1 and P2. Those can be dispatched to two different multipliers. P3 can't happen in parallel. Right? P3 can only happen after both P1 and P2 are available. So if we look at this over time, A times C and A times B can be in the pipeline. Okay. Then, once that happens, and A times C is available, we now can multiply P1 times P2, and those can go through. So our program sort of has two phases, right? The first independence phase, and the second phase which is dependent upon that. Instructions take a certain number of cycles. Okay? It takes 3 cycles to do instruction. It takes 4 cycles to do instruction. They also have to be dispatched with a certain latency. That means spaced a certain amount apart. And the compiler knows these rules. I'm sorry, and the processor knows these rules. And so it's going to make sure that when it dispatches things, that they're scheduled properly. Okay. So in this particular generation of the processor, one load with an address computation, one store with an address computation, 2 simple integer operations, 1 complex integer operation being a multiply or divide, 1 floating point multiply, and 1 floating point add can all be done at the same time, simultaneously. Those are our basic functional units. Okay? But some instructions take more than 1 cycle. So latency is how many cycles? Okay? Cycles per issue, okay, is what the delay is. All right. So here we have a loop, and we can just see in the case of multiply what the cycle counts are. Now, this is looking at doing this. 1 times DO. the result times D1, the result times D2, the result times D3, the result times D4, the result times D5, the result times D6, the result times D7, right? That's a long chain of events. Sequential dependence. The second multiply can't happen until after the first. So the performance is determined by the latency of the operation, how long each one takes. Okay. If we unroll this loop, x times dy plus dy plus 1, something like that. Okay. And do more work per iteration of the loop. Do more work in parallel. Now we can find that this, right, achieves a better latency bound. Let's take a look at why. Should have a slide here. Here we go. Okay. Now we can see that I'm getting some parallelism. You see these operations are not stacked straight down? I can sort of get two operations side by side. D0 times D1 and D2 times D3. D4 times D5. And then I can multiply those results. The result, D0, 1 times D2, D3. Or D0, D1 times 1. That quantity times D2, D3. That quantity times D4, D5. You see that? So now I'm getting things in parallel. I'm able to use more functional units at the same time. Here I'm using separate accumulators. Notice that I have two variables now, x0 and x1. This is going to give me a little more independence, because it's not dependent on the same accumulator. So now I see this. Right? These two streams don't get tied together until here. Nice, long, independent chains. So what are the ideas here? Unrolled, make it as wide as we can. Accumulate in parallel, right? Use separate accumulators. Of course, there are diminished returns, right? There are only so many adders I have. There are only so many multipliers I have, right? Once I'm making use of all my functional units, right, I've exceeded the parallelism the processor has. What happens if I unroll? And I have, some odd number of things, right? If I unroll and I do 4 units of work per loop, and I have 7 things, or I have, 17 things. Well, I'm going to get 4, 8, 12, 16, and I have 1 left over. I have to deal with that one separately. If I have 19 things, 4, 8, 12, 16, I have to accumulate those 3 at the end separately. So, I need to finish off sequentially. So for short bursts, it may not be worth it. For longer bursts, it may be. Okay. Too long bursts, again, we lose because we've saturated the functional units. Here we can see the number of accumulators on the left, the unrolling factor on the top. Okay. And again, enrolling factor, instead of processing 1 iteration per loop, right, we'll process 4 iterations per loop sequentially, and just move in the units of 4. We can see that our best performance is here. Going left, we're not unrolling enough to take full advantage of the parallelism. Going right, we're accumulating overhead, doing that we don't need to accumulate because we've already saturated our parallelism, right? Same thing with going up versus going down. More accumulators is more work because you have to add the accumulators, right? If you already have enough accumulators to be parallel, adding the accumulators is a waste of time. Okay. So ultimately, if you can find this type of data dependence and get rid of it, you're limited by the throughput of the number of functional units. You can't do more work per unit time. The processor has the ability to do work. In the original example, we've gotten up to 29 times improvement over the original unoptimized code. Way better than just the 2 times improvement or whatever it was we saw with simple O minus O1. There are specialized instructions that are designed to handle doing the same operation multiple times, okay, on a vector. These are the SSE instructions. They were obviously added to support streaming and things like that, okay? So you're going to get better performance if, when you compile, it makes use of these than it doesn't. Branches are a pain in the neck, right? Jumps. When we encounter a conditional branch, we can't reliably determine where to continue fetching. If we can't reliably determine where to continue fetching, our pipeline can stall. Do I take this instruction or this instruction? If I don't know the answer, right, I can have to wait until I evaluate some variable to determine what's going on, and then figure out my stream. And just stall my pipeline in between. That's a problem. The other thing I can do is guess. Assume that the branch is taken. And if I get the guess right, then I've saved a bunch of work. I haven't stalled. If I get the guess wrong, everything in my pipeline, everything in my retirement unit has to get flushed and I lose all that work. I can have statistical branch predictors built into my processor that attempt to guess in more refined ways. Okay. I mean, so to some extent, you could also do both branches, right? And then keep one of them. There's nothing intrinsically wrong with that approach. I think the problem there is you're chewing on exactly the same data, but you can copy it over and do that, I guess. There's no intrinsic reason you can't. Okay. Guess which way the branch will go. Begin executing instructions at the predicted position, but don't actually modify the register's memory. In other words, inside the processor, we have shadow copies of these registers, right? We have this because it allows us to have, for example, multiple threads in flight, right? It allows us to do things independently and combine them at the end. So that's the purpose of the retirement unit, to commit these things to the physically real global set of registers and memory only once the order is known. So what we can do is we can use these shadow registers and then throw them away or not, and we figure out if we're right or wrong. Okay. Of course, if we get it wrong, we throw away a lot of work. Oops. Performance cost. The performance cost of mispredicting is multiple clock cycles on a modern processor. It actually can be a very significant performance limiter. Mispredicts really waste a lot of work.
Wouldn't that work be wasted anyway because you have to wait for the results?
The work would be wasted anyway, but we have to wait for the results. But the problem is that modern processors get so far ahead of themselves that you're losing a lot more work one way or the other than you think you would. Then on a simple processor that fetched, decoded, and executed, there's no width there. So you're not losing anything. Does that make sense? The penalty is sort of counterintuitive. So if we always predict a branch is taken, right? That's the simplest strategy that's sort of useful. Then what happens is, on typical if statements, I'm right half the time and wrong half the time. But on loops, I'm only wrong once. The end of the loop. So what do we need to do to get high performance? We need to have a good compiler that knows a lot of tricks. We need to ask the compiler to use those tricks, optimization flag. We need to avoid doing things that are silly, like picking the wrong algorithm. Okay? We need to write compiler-friendly code. That means avoiding aliasing, inlining functions where it makes sense, things like that. And we need to focus our optimization on the innermost work loops, Amdahl's law. Focus our effort on the code that's used over and over and over and over again. Exploit instruction-level parallelism. Avoid unpredictable branches. We prefer branches that are taken, right, or things that can be easily predicted by a statistical predictor. And make code cache-friendly. Okay? Any questions? Have a great day, everybody.
Wait, what? We really optimized this lecture. How?
that